Hello again, grade 7s. In today's lesson, we are going to wrap up the unit of study on probability by drawing a comparison between experimental and theoretical probability. With our learning outcome to conduct a probability experiment to compare the theoretical probability and experimental probability of two independent events. We're not necessarily in this lecture going to conduct an actual experiment as much as examine a probability experiment that compares the two things. But let's jump into trying to define them. What's different? What is experimental probability and what is theoretical probability? Theoretical probability is the expected probability of an event occurring. So this is mathematically what is actually supposed to happen. For example, the probability of flipping a coin and landing on heads should be 1 out of 2, or 0.50, or 50%. Theoretically, this is what's supposed to occur. Now, experimental probability is a probability of an event based on what actually happens. Because here's the thing, even though the theoretical calculation tells you that 50% of the time you should get heads, this may not always be true. I mean, and you could actually conduct a really simple experiment of this with a coin. You could take a coin and you could flip it 20 times. Now, theoretically, you should get heads 10 times and you should get tails 10 times. It's a 50% chance of getting each of them. Although I guarantee you, or maybe not guarantee you, but it's very, very likely that if you flip them, you're going to either flip heads more times than tails or tails more times than heads. Okay. Something a bit differently is going to occur when you actually perform the experiment. The example I said here is an unlucky person could flip a coin 100 times. And again, theoretically, we should be getting heads 50 times and tails 50 times. But they could easily go ahead and do this and only get heads 30 times and tails another 70 times. So something's not matching up. What's supposed to occur in theory is actually not occurring experimentally. In that case, the probability of getting heads would be 30 divided by 100. So you'd identify the number of times you actually get heads divided by the number of times you flip the coin. And that would be 0.30, or converted into a percentage, it would be 30%. Let's look at an example problem where we actually are going to calculate this. A student flips a coin twice, and they record the results in the table, and then repeat this experiment for 100 pairs of coin flips. So here's what happens experimentally. They flip a coin one after another, and they repeat this 100 times. So when they do the experiment, they get heads followed by heads 21 times. They get heads followed by tails 25 times. They get tails followed by heads 28 times, and they get tails followed by tails 26 times. This is what actually happens. This is going to be our experimental result. The first thing I want to do is I want to calculate what is the theoretical probability of flipping two tails in a row. Now, the theoretical probability has nothing to do with what actually occurs. Okay, it's a prediction about what's going to happen in advance. So when we calculate theoretical probability, we're not going to use the results of the table at all. We're going to perform a calculation just like we did in the previous lessons. So if I wanted to calculate the theoretical probability of flipping two tails in a row, those are two different independent events. I'm going to start off by drawing a quick tree diagram. So my tree diagram would be pretty simple. I would have, we'll say, flip number 1. And on flip number 1, there's two possible outcomes. Either you get heads or you get tails. And then event number 2, flip number 2. There's two possible outcomes. On flip number 1, you can get heads followed by heads on flip number 2. Or on flip number 1, you can get heads followed by tails on flip number 2. If you get tails on flip number 1, you could get heads on flip number 2. If you get tails on flip number 1, you could get tails on flip number 2. Now, I want to calculate the probability of getting 2 tails in a row, so I'm going to write down the probability of getting tails followed by tails, and that's equal to the number of favorable outcomes divided by the number of possible outcomes. Now, we're not using the results from the table here. This is what actually happens, but theoretically is a prediction I make in advance. So I use just the tree diagram to identify that. Okay, how many possible outcomes are in the tree diagrams? We'll count the number of branches. There's 4 of them. How many ways can you get tails followed by tails? 1, okay? There's only 1 favorable outcome. So the probability of getting tails followed by tails, theoretically, is your favorable outcomes over possible outcomes, which is 1 over 4. And if we convert that into a decimal, it'd be 0.25. And that would be equal to 25%. Okay, so theoretically, if I flip a coin one after another, I should get tails followed by tails 25%. Now, experimentally, this does not happen. If you look at the table here where the student actually performed the experiment, this happened 26 times, not 25 times. So we want to calculate the experimental probability of flipping 2 tails in a row. So to do this, we'll write down the probability of getting tails followed by tails. Now, we're going to write the formula out a little bit differently right here. I'm not going to write down favorable outcomes divided by possible outcomes. I'm going to write down number of times desired result obtained divided by the number of times the experiment was performed. Okay, so let's look at this. How many times did we perform the experiment? Well, they did this flipping of a coin followed by flipping of a coin 100 times. Okay, this experiment was done 100 times total. Now, how many times did they actually get, in reality, tails followed by tails? That happened 26 times. So this would be 26 over 100. 26 over 100 would be as a decimal 0.26. And if you convert that to a percentage, you would get 26%. Now, C wants me to compare the two. How does a theoretical probability compare to the experimental probability? Well, let's take a look at this. The experimental probability of getting tails followed by tails was 26%. This is what actually happened. The theoretical probability of getting tails followed by tails was also 25%. So the experimental probability of getting tails followed by tails was slightly larger than what it was theoretically. Pretty close to the same, but slightly bigger. So let's make a statement here. I'll say the experimental probability is slightly larger than the theoretical probability. Oops, I don't know why I did a vertical line here. Let's get rid of that. Experimental probability is slightly larger than the theoretical probability of obtaining tails followed by tails in this experiment. Now, I should point out that as you repeat this experiment more and more, so let's say that we actually perform this experiment maybe like 10,000 times or something, you're going to start to find that the more times you repeat the experiment, the more the experimental results are going to get closer to the theoretical ones. I suppose the reasoning is that there's kind of like more trials for things to like offset each other. If you only perform the experiment like a few times, there's not enough time or not enough trials to get like that kind of that even distribution in terms of expecting each result 25% of the time. The more times you perform the experiment, you're going to get closer to the experimental results matching up to what should happen in theory. So that's it for the end of this unit. And you can conclude it by completing on pages 187 through 189, numbers 4, 5, 9, and 11. And again, just a quick little word of caution again. Anytime when it's asking you to calculate theoretical probability, you're doing it based on what you predict happens in advance. So if it provides you with a table of what actually happens, the theoretical calculation has nothing to do with that. Okay, the theoretical calculation is based on a tree diagram you construct based on the independent events. The experimental probability would be dependent on looking at a table of actual results that are obtained. And as long as you can make the distinction between those two, you shouldn't have any issues with this particular assignment.